All right.
Yeah, we're good. We're
Uh,
on.
okay, cool. So we're under the selectors section right here, 7.2.
And I have us
Yeah.
in the
Um
Hangouts so we can all sort of,
oh, we can all share.
yeah, because
Oh,
the
great.
other one, and we have like the chat there too and whatnot. So, um,
Cool. So I think the biggest takeaway from selectors is, it relies on just specifically placed unit vectors in its A matrix. So I think the first example with like the time series and skipping every other one every 2 hours, was simple enough. Every other vector is a zeros vector. And then you have your unit vectors as well. Um, this one was the same image cropping, the same concept, but just a little bit more difficult. So John and I talked in depth about this one. Do you remember this one, Michael, or no?
Yeah, I remember it, but I didn't like get that one. I
Okay.
like skipped because I was like, I know it's gonna be super complicated, and when I need to do it, I'll have to go back to it. But
Yeah. So the
I think
idea
we're
here,
probably gonna end up doing it in Julia, is my guess, which is
well, I
annoying.
have it. I got the right matrix actually, John, and I did the multiplication, and it all came out
Oh,
correctly.
good. Wait. So hold
So
on, hold on. So is that what we're saying? So like, so you should have a
yeah,
5.
can you do it in a Jupyter notebook? Like copy it over so that
Do
way.
you have that
yeah.
scene?
I mean, I don't have Jupyter notebooks set up,
You have Atom.
but
Maybe do it in Atom, and then we'll move it over to Jupiter or
yeah,
something.
I mean, unfortunately, my Atom. I
Okay.
know. I'm
All
sorry,
right.
my
You
Atom.
can install
I'll show.
Jupyter
I'll
right
show you.
now. It doesn't take very long to do.
Hold on.
Uh,
Let me. My Atom was working good for a while, but John saw before. It's now there's like something got uninstalled or something. It
And
it
keep in
freaks
mind,
out.
this isn't really the Julia side, so we're gonna do the real Julia side.
Yeah. So I
So I
don't know
wouldn't
if
go crazy about it. I think Shane just wants to
I just
display it
wanted
so
to.
we. But yeah,
Yeah, I just
Jupiter would
wanted
be
to show you
easier.
guys. I just wanted
But
to
I
show
want to
you
see
guys
that
what the note.
matrix though, because what I'm envisioning is basically, so it's got to be 25. So this, wait, what size did you use?
It's
The
this.
100.
Well, before we get into that, can we explain to Michael just our thought process of every so he can
Yeah,
like
yeah. Maybe you should
so he
show
can
him
yeah,
your.
see
yeah.
it?
Maybe show him
Yeah.
your document that you drew.
So
You drew.
um, I don't know if I
Oh, you don't have
have.
that?
Oh
Okay.
yeah.
All
Okay,
right,
my
that's no,
handwriting's
but that's
freaking
good. No, but it's
my
good.
hand freaking terrible here. But the important ignore all this. The important part right here is this section. I'm
But
sorry.
before you get into that section, on the top right of his screen is an image, and it's broken into quadrants. And what we're really looking for is the top left
Top
quadrant.
left quadrant, right?
Yes.
Yeah.
So all the pixels go from 1 to 100. It's we did an arbitrary like 10 by 10. So if you would just imagine, you just wrote them out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you did that all the way to 100. These are the ones we want. We want the 1, 2, 3, 4, 5, and then we would skip the first quadrant.
So
Then we want the
x is
11 to
a
15.
sorry. Yeah. So x is a vector of 1 to 100 basically.
Yeah. And the way I mean, in reality, in their see, there's a lot of points to get confused here. But in their example, that X would be a vector of like 100 RGB values because they're pixels. In
Yeah,
this,
yeah.
but we just did 1 to 100 for so you can like so you can see the order. So you would end up wanting these. I have an index array right here. So out of X right here is 1 to 100,
So
right?
so
So
just to
listed 100
clarify,
elements.
yeah, yeah. So you take the first 5. So every row is 10 elements. And for every single row, you only want the first half of them until you get through half the rows,
Yeah.
which is the quadrant, the top left quadrant.
So I wrote index here. This is what we're trying to we want to get like 1, 2, 3, 4, 5, 11 to 15, 21 to 25. So then we ended up creating, so our X is 1 to 100, right? Like this. And we ended up creating, A would look something like this.
I
And
can't see. It's too small. Let me
oh,
I'll make it bigger on my end.
let's see, can I control plus
It'd
here?
be nice
No, I
if
can't.
you, Shane, if you didn't have. The problem there is you can't really. So I can see the 25 rows, but the problem that you have immediately is that you have no ones anymore. Like as soon as you get past the first 5 of them or something like that. or whatever.
Oh, yeah, yeah.
You know what I
So
mean?
the fifth one, what you're saying right here. So
Or
it's
whatever
like
it is. You know what I'm saying? You can see the start of the
Yeah.
next one because you're
but you can
skipping.
actually see
Yeah,
the
you can
ones
see the
over
start of
here.
it. So that must be
So
11.
it's skipped. Yeah, it is. Yeah, so 5, 6, 7, 8, 9, 10, 11.
How many
Right.
pixels are you trying to select?
So we're trying to select a
quarter
quarter
of
of the
them.
whole image.
A quarter of the
Um,
whole image.
So that's
Yeah.
why that's why it's 25. And just we
okay.
can we,
20.
we can
This is a 25 by 25.
No,
this is actually
That's the
25 by
thing.
100.
Yeah.
Okay.
So we can look at new A, but it might just be helpful to show you the multiplication A times X first, and then you can see what Y is.
So
And
this
then
should
Y,
match
you
the
actually-
index file, basically.
Exactly.
The index one that Shane made.
And
And it
actually
does.
it does here. So
So X is 1 to 100.
yeah.
New A is that matrix up there. The multiplication of those two gives him.
you end up getting the appropriate pixels.
Yeah.
Which is this, yeah. So yeah, I mean, hopefully this visual makes it a little bit easier.
The visualization really sucks. I mean, to be honest, it's really hard
Yeah.
to.
No. It's fine. You just select it. You apply the selector matrix. To
Yeah.
select a quarter of the image.
So let's just
Yeah.
talk about really quick before you move on, Shane, where the ones actually are in this.
Yeah,
this
yeah.
matrix. So each row is a unit vector, right?
Mm-hmm.
So the selector matrix works like that. So in our case, we want the first 5, right?
Yeah.
But then we want to
So
skip the
then-
next 5, and then we want
So
the
that's-
next 5,
yeah.
and then we want to skip the next 5, like that.
Yeah.
So which is why you just
So
see
you
a
can-
bunch of zeros.
Why do we have
You
to
s-
do that instead of just having a straight diagonal?
Well, first of all, there
If-
is no
so if you had a
straight
sh-
diagonal.
It is straight. It is a straight diagonal.
It is. No,
No,
he's right.
well-
It is if you look at just that little tiny piece of the quadrant of the matrix.
Yes.
But there is
yeah.
no
So
such
the
thing
first
as a straight.
5.
There is no such thing as a straight diagonal all the way through because this is a 25 by 100 matrix. First of all.
Yeah.
And I think John had a good way of explaining it when I was talking to him. It's like a bunch of 5 by 5 identity matrices put together, right?
Right.
So you have the first 5 identity matrix right here, and then you have to skip some because you don't want those pixels, and then the second 5 identity matrix starts right here, actually at 11, and then
Right.
you would have another one that starts at 21. So it's a bunch of these perfectly placed identity matrix to get the exact ones you want.
Right. It's actually almost the same thing.
Why do we have to skip them? Let's go back to that formula.
Yeah, that's what I was going to
Yeah.
say. It's almost the same thing as the original selection matrix. It's just that in this case, you're not going every other one. You're well, I guess you kind of almost could look at it like that, but really what you're doing is you're picking a group of 5 and then you're skipping some amount, picking a group of 5, skipping some amount, picking a group of 5, skipping some amount. So it's very similar to the selection one.
The reason you're skipping them, right, Michael, is just because, like, if you see on my diagram over here, we have to skip the 6 to the 10. We have to skip the 16 to the 20. You have to skip all. We don't want any
the
of
selection
those.
matrix.
Oh, because they go straight across.
Yes.
Okay, that's why. Then.
Yes.
And then once you get down here past 50, you skip all of them.
Yes.
Yeah.
Which is why the bottom right of your matrix just looks like a bunch of zeros. If you look at your the one you have on the screen, that's why the whole right side of it just looks like friggin' zeros.
Oh.
You know what I'm saying? Because
Yeah.
because those represent, they everything from that 5 by 5s that you have, Shane, is only going to shift down to half the matrix. So can you show new A, like you have transpose, but just show columns?
That's actually what A is.
What?
A is just for better notation. A is actually new A transpose. That was just because of how I said it.
All right.
So
Can you just show half the columns? So
what is that? That's like just
50 of them.
50 like
so
that.
just
So how did you
well-
build? What formula did you use to build this new A?
Oh well, we had to come up. Well, I mean, they explain it right
wrote,
here.
Michael, I actually wrote one.
That's what I'm wondering.
Yeah. It's
So-
worth it. It's worth the exercise.
Yeah.
But Shane, can you just do colon, comma, and then the colon 50 like you have?
Yeah. Hold on, bring it
You're
up.
almost there. You just have to just put a colon.
Colon, comma,
Yeah,
and then the 50
yeah.
like that,
And then a
right?
colon,
Yeah.
and then colon
Oh.
50. Colon 50.
And then colon-
No. Just
colon,
delete.
comma 50.
Just hit
Oh.
delete, and then put a colon in front of the 50 as well.
Oh, like that. Oh,
Yeah.
okay.
How do we do it? How do we
No.
do it? We need all the rows, and we need up to 50 columns.
You need the first 50 columns.
Yeah, but we need all the rows. How do we do that? Is it? Can you try one?
Can you just do you even need the? Can you just do this? Yeah, fit. Let's do. You do no.
We'll do that.
Like, I didn't find that paragraph very explanatory.
Oh, there you go, John.
Wait, how'd you? Yes,
Okay.
that's yes. It was just the one that we were missing. What the hell? Is this right? Yeah, I guess it's right.
Yeah, that's right.
I
This first 50.
expected, honestly. Okay, can you just do 25 then? Okay, yeah, the ones go all the way to the right on this one. You see? Oh, they do in
Sorry,
the 50.
right
They
here.
do, okay, no, the 50 was correct. Okay.
No, they won't, because like the way that it
Right, but
you
the
have to do it.
right,
Yeah.
but the 51 was correct. If you look at the 50 matrix again, Shane, if you put that up there.
Yeah.
But what function
you go.
did you use to build A?
Good question.
Yes, I mean, so first they say it in words, right? And this was, it's not exactly the clearest. We had a few functions to build A, and we built it wrong a couple times too.
But I personally, I did a little bit of it too, Shane, on my own, and I found that like I just had to build I did the same thing that you did for the ones vectors, except I didn't use vectors. I used matrices, and I just said, I just stacked. I just stacked a bunch of matrices together because these
were
are
actually
all identity matrices with a bunch of zero matrices. So that's
we
how
were
I did
we were
it.
right.
A is
I didn't have to.
MN divided by 4 times MN.
Yeah,
Right.
so that's why the length of it is 100, right? But then you get 25
The
by
length
100.
of it is the entire vector. Yeah.
Yeah.
So this is for selecting the upper quarter.
Yeah. So obviously you'd have a different.
I mean, you
have a
don't. This is
different
the size of it
to
is just
calculate.
for selecting a quarter of it. But what Shane did was selecting the upper quarter of upper top left quarter of it. But you can just alter the indexes like he did on the X vector or was it the X vector? What vector?
Yeah. Conceptually, John, we were actually
the
like
A matrix. Yeah.
the X. Conceptually, we were actually pretty correct the first time. I didn't have to do like any magic. We just like didn't transpose something at a certain time or something. How did we construct A? We basically did it backwards. I think we actually used the index. We used this index vector. We did like reverse engineering of it, kind of.
Honestly, I think it's worth it that every you just try to build this on your own, because there is a bunch of ways of thinking about it. Shane is going to do it a little bit differently than me. I'm going to do it a little bit differently than you, Michael. So I think it makes it worth it to just think it through and how you would build it through.
Yeah.
But I also think that it's going to happen when we do the Julia side. I'm going to bet anything they're going to make us do it, and they're going to show us the slickest.
When we get
way.
down to convolutions, you're going to have to use the same math.
Right.
Because convolutions have something called a stride.
Mm-hmm. Yeah.
The stride is like you have this box, right, and it's floating on top of your other matrix. And the stride is the width of that box, the amount that you move the box around.
Like a window.
Yeah,
it's like a window. Yeah.
Interesting.
Yeah, if you're interested.
So it's probably a selector matrix.
Right. That makes sense. Yeah, that sounds right. Actually, that sounds like something.
Yeah, if you're in, which. Yeah, I mean, this was like the main function we used, Michael. Just
yeah.
So we
what
had.
What is the 100? Oh, 100.
The length. That's just the length. Yeah.
And then.
And then you end up getting this, and you just
hold on. He doesn't know what unit is. You made that up.
Oh yeah. I forgot about that. Unit is a function that takes in the length. And you can just give it an index, and it'll put a 1 at that. So if you wanted to put an index,
it just makes a unit vector at an index. Yeah, it's not,
yeah.
So
exactly.
he just vectorized it over
over all the specific
all the specific indexes
indices.
that he needed a vector. Yeah,
Yeah.
exactly.
Yeah.
So
Yeah, it's not too bad, but they gave a pretty short section right here to explain it to
yeah,
us.
I think this book like they
Uh,
expect you to just know a lot of things. And when you really understand it, then you read what they wrote. You're like, oh yeah, that makes sense.
Yeah, they worded it exactly right here. They only gave us like one sentence though. The
But we were
ith
like,
row of
what?
A is
Yeah,
the
what are you
unit
talking
vector.
about?
The unit vector for the pixel in act. Yeah, exactly.
Yeah,
But
and once
anyway.
you understand it, you're like, oh right, yeah, of course.
Yeah,
but
yeah,
it's
yeah.
just a weird thing.
Well, it
Yeah.
would have been nice if they showed A actually, just like they showed A up here. But I guess it's a more complicated A. So
It's going to be the same for the convolution.
yeah. Okay.
Maybe they have a faster way of doing
Wait,
it.
do we come up to that in the? Is that in the book?
That's 7.4. So
Oh, okay.
But doing a convolution is the same thing.
Okay. Cool.
It's you have to create a selector matrix, and you got to keep convoluting, which means moving it around.
Interesting.
Yeah. Yeah, that is interesting. So I guess they're giving us the tools to do that first.
Yeah.
Okay, permutation matrices. Sounds like this is applicable to that as well.
This is probability.
And n by n permutation matrix is one in which each column is a unit vector, at each row is the transpose of the unit vector. Okay.
What?
Each row is the transpose of the unit vector. Can you even? Oh, okay. Okay.
I mean, wait, what?
In other words, yeah, I didn't realize.
An n by n
It's
is
a square. It's a perfect
Which each
square.
column is a unit vector, and then each row is a transpose.
It's n by n, so it's a square.
Yeah.
So you're just gonna have all the diagonals. That's all.
So whether you look at it by rows or columns, you have a unit vector both ways. There's only ever going to be one.
So
in
is
each row
that
or each
pi
column.
312 telling you where the ones are? It's in the third column. The
Yeah,
first
I
I
see.
column.
usually
Yeah, third.
denote
One. Yeah, that's what it's
probability.
doing. This is saying the third one for the first row, the first index for the second row,
Okay.
the second. Okay. So let's see here. So this means that y equals ax can be expressed as yi equals x pi I, where pi is the permutation. Each integer from 1 to n appears exactly once. Okay. So as a simple example, consider the permutation 312. The associated permutation matrix is this. Multiplying a 3 vector by A reorders its entries.
What the hell?
So-
I don't understand what this actually does.
So if you use that as a selector matrix, it would select the third value
Hmm.
in the first.
Oh, so
X-
I see what it.
yeah.
Oh, it selects a
First
specific.
value
Yeah.
in the
It
second
selects a
row.
specific permutation of the
Yeah.
thing.
That's
got you.
interesting,
Yeah.
and that's probably pretty useful. So x is x1, x2, x3, obviously. You
That should
multiply it by this.
technically be that. Well,
Yeah,
I guess that's
yes.
how you wrote the function anyway. So
Yeah, that's interesting. It's almost got like group theory
Uh,
application to
no.
it or something.
uh,
Probably does.
Dad. Oh, never mind. All right.
That's cool. Yeah, I like this. This is cool.
Yeah.
Okay. Incidence matrix. Directed graph. Directed graph consists of a set of vertices labeled
So the
one.
incidence matrix is basically that same thing. You have nodes and you have edges.
Each edge is connected from one of the nodes into another. Okay.
Except the difference between an incidence matrix
Directed graph.
and the what was the thing above it? The selector matrix. Is
Yeah.
this one has direction. So you
Okay.
can make an arrow like it's flowing into the second node.
This is called.
Yeah.
They're calling it incidence matrix. Is this like an adjacency list or adjacency?
Yeah. This is literally, it has a direction. So you have -1 if it's flowing out of
Oh.
something and 1 if it's flowing into something.
Oh, so it's just
Yeah,
in edges
yeah.
and out edges. Yeah. Okay.
You could do it, and it says in here that you can do it with a selector matrix, but Yeah, hold on. I gotta tell him to bring me food. I'll be right back.
All right.
All right.
So in the
Okay,
case
so
here
yeah,
1-1, it says I points to J.
so I points to J, edge J. Oh, from node I. Yeah, exactly.
And then
What you
any
just
other
said.
one like.
So here,
I mean, this is
here
basically
you have
just
J
how
points to
you would
I.
build a graph off of these.
Yeah.
You're just building a
Yeah,
graph
that's
structure.
so it's literally
Network
okay.
X actually
Cool.
actually does this for you. Like,
You
not
can
does
turn
it
it
for
into
you.
this,
Well, if you gave
a
Network
matrix.
X, a matrix like this, and you could give it like, you don't have to use the column vectors and column rows, but if you gave it a matrix like this, it would build the actual graph structure for you. I forget what. Let me just see.
Yeah, that's neat. That's neat.
Yeah. So one is a network graph without there's no in and out.
And undirected, right?
Actually, yeah, in
Undirected.
an incidence matrix. So what does it say right there? You can have self edges. So you can have a node flow back into the same node, but in the adjacency matrix, you can't do that.
So this would be along the diagonal, right? So this first -1, you have 1 points to itself, right?
Yeah.
So the direction when it points to itself doesn't actually matter.
Well,
right?
Yeah, it doesn't matter. You
So
can do it with a selector matrix. That's an incidence matrix.
But
So a
share my
selector
screen, it won't
matrix
kick
would
you.
just be all the nodes by all of the nodes.
So my question though is, if I and J are the same, like along the diagonal, does it matter if it's 1 or -1? Those would be exactly the same. It wouldn't affect the graph structure at all, right?
Well, that's the difference between an adjacency matrix and a incidence matrix. So the incidence matrix is literally all the nodes that you have by all the nodes, and then you fill in 1 for the intersections. But this one has direction, but you can't feed the same node back into itself.
Right, adjacency would just tell you where those rows point to, but this one's telling you which one points to what. It's kind of interesting, actually.
Yeah.
I'm sharing how Network X does it. This is the graph library that we're using. And it just literally, I could take that graph, Shane, and I could turn it into this. And it'll just give me every node.
Yeah, I would totally.
Yeah, I mean, I guess this is pretty standard notation. I mean,
it is.
Totally
it's standard notation for graphs. It is. Like, they have the same kind of notation with a sparse matrix because of obvious reasons. Because you don't need to store all those zeros or whatever. So they'll just give you like an edge list. So this isn't a like incident matrix, but they could give you an incident list of edges, and it would be something similar. Yeah. But the problem with that is you would have to store the direction, right? So you would have to say, so usually like in adjacency list, you'll have something like node A, right? And then you'll just have a list of edges that node A points to. And then, but in this case, if I wanted to store it as incidents, I would need something like, I don't even know how you would do it actually. Without a matrix, I don't.
Well,
I guess you could just do it the same way, but you just point. You just have the index and the value, really.
Yeah. See, like, there's this other thing you guys should probably know about. So this is where you start to get into eigenvectors. So say you had one categorical variable by another categorical variable, right? If you take the eigenvector or the eigenvalue of each row of that matrix and you reduce it, when you sort from highest to lowest and lowest to highest, the lowest eigenvalue system is going to give you the least complicated graph. And then it's like when you don't know what the edges are. You know what I'm saying? So say you had like two numbers and you wanted their relationship to one another. This makes more sense in the realm of like convolutions, but doesn't make as much sense in the realm of what is my most complicated network? What is the simplest network that I could form?
Yeah, I mean, I don't fully get it, but it kind of makes a little bit of intuitive sense. But they touch on that. And,
No, well, they only touch on the convolutions. They don't touch on the.
like it sounds the lowest eigenvalue having the simplest form of the graph, and then I guess.
Yeah, exactly.
Yeah. All right. So are we good to go? Networks.
Yep.
All right, in many applications, a graph is used to represent a network through which some commodity or quantity, such as electricity, water, heat, flows. The edges of the graph represents the paths or links over which the quantity can move or flow in either direction. If x is an m vector representing a flow in the network, we interpret xj as the flow rate along the edge j, with a positive value meaning the flow is in the direction of edge j, and negative meaning the flow is in the opposite direction. In a network, the direction of the edge or link does not specify the direction of flow. It only specifies which direction of flow we consider to be positive.
Yeah.
Wait, that last sentence there. In a network, the direction of the edge or link does not specify the direction of flow. It only specifies which direction of flow we consider to be positive. Do you guys understand that or no?
No.
Are they talking about the edge weight?
That's what I was wondering if they're talking about weights in there, but I'm not really sure.
The direction of the edge is indicated by 1 or -1. Or link does not specify the direction of flow. Well, I thought that's what the direction of the edge was.
The rate. I mean, that sounds like a weight.
Yeah, it does sound like a weight. Like, imagine those weights could be minutes. Like, if you just had a GPS coordinates, the weights could be like minutes instead of weights.
Oh, okay. So yeah, I think you guys. So it's on the edge, right, of the graph. So it's like a weight. That's like kind of what a weight is, right?
Yeah.
But then I guess their only point is you don't, like, if you imagine a graph, there's no arrow pointing to either direction of the node. It's just a positive or negative weight.
Yeah, I guess that makes sense. So when you move down into the networks, they don't use the what is the other one called? Incidence matrix, adjacency matrix. I guess they don't use an adjacency matrix. Instead, it's like a value of some arbitrary unit. So instead of being -1 or 1, I guess it's like a value of a unit.
Yeah. It can be a specific. It can be any number, right?
What is flow compensation?
It doesn't have to be 1 or negative. Yeah. So it can. So they're saying it can go in either direction. So the direction doesn't matter, but the weights, which they're calling the rate along the edge, can be positive or negative, with a positive value meaning the flow is in direction of the edge j, and a negative meaning the flow is in the opposite direction. So they're using the weights to kind of make this not directional graph directional.
Yeah.
I don't know. That's my interpretation, at least.
Yeah. I mean, if we hurry up and I get through this, though, I can go out to eat with them. So
sorry.
Let's just try to like get through.
Yeah. It's like a little bit more confusing than maybe past stuff.
No. So they're showing you like harder ways of doing it, but really like the network is like it's the way that I would do it.
Okay, flow conservation. When x represents a flow in a network, the matrix vector product y equals ax can be given a very simple interpretation. The n vector y equals ax can be interpreted as a vector of net flows from the edges into the nodes. yi is equal to the total of the flows that come into node I.
So it determines the thickness of the line.
The quantity.
Basically.
It's a flow surplus. If at x, we say that flow conservation occurs since at each node the total inflow matches the total outflow. Wait, do they give a diagram of this? Is this the same network with 4 nodes and with source flow shown. Like a net positive flow, or is this diagram what they're talking about? Do you figure it doesn't look like it, right? Network with 4 nodes and 5 edges with source flow shown.
Yeah, those are the S's, right?
But is that what they're talking about up here with like y is equal to total flows
Well,
minus
this is more like a pipe network
from node I, sometimes called the flow
than
surplus.
anything. I don't know.
In this case, the flow. In this, wait.
This is like water. If you put something into the system, it has to come out of the system.
It's going to be used as traffic. Yeah, like water, traffic flow, and with the nodes representing intersections at the edges. Describe the directing graph. Yo, I don't know why, but like I'm like super confused.
You're confused? So like
yeah, I don't really understand.
It has to have an in to have an out.
Yeah, I mean I understand like that part, right? The conservation, I guess. There needs to be like a net zero or something of inflow and outflow. But I guess I understand like a piping system or traffic.
Yeah, it's like a traffic system.
So in this case, does everything go to 4?
It has to eventually, right? Because 4 has no out.
Yeah, I guess everything goes into 4. But I don't think it needs to net to 0. Can't 2 continue to have a value?
Can't 2. Oh, it doesn't need to net to 0. You can just keep.
You can retain some of the water in node 2, I guess.
Well, so in this case,
because I don't see an out.
In this case,
there's only sources. There's no outflow.
There's no outflow here, so you can kind of get like an infinite inflow, based or not an infinite.
It distributes somehow.
So would the inflow then be S1 plus S2 plus S3 plus O is 0? Am I thinking of that correct? Because eventually, all of those
and a certain amount based on the weights is going to end up in 3, 2, 1.
Okay. I think this is clicking a little bit more.
But I think this sounds like something I would use like something pre-built.
Okay. So we have a surplus here then. Do we have a flow surplus of S1 to plus S2 plus S3 plus S4? Is that correct?
The quantity yi is sometimes called the flow surplus.
Oh, and no, that's the at a specific node.
Yeah. At node I. So it has
so
a flow.
We're at this node.
Yeah.
What would so
in this case the flow vector x is called circulation.
In this case, the flux is called circulation. This could be used as a model. Okay. Oh, here we are. Okay, so let's see. So for a network described by directed graph, example above, the vector 1, -1, 1, 0, 1 is the circulation. Since AX equals 0, this flow corresponds to a unit clockwise flow on the outer edges and no flow on the diagonal edge.
Where's 5? Oh, X5.
1, 3, 5,
the
and
edges,
2.
yeah.
Why is there? Oh, there's no
1,
flow on the
3,
diagonal
5,
edge because that's
and 2.
X4.
No flow on the diagonal edge.
Because it's X4 is 0.
Oh, because X4 is 0. Oh.
X is the edges.
Yeah. Okay.
So you have like, let's just think of how we would do this without the book. But you have one array that has 1, 2, 3, and 4 in it, and then you have another array which has all the edges. It's like having two separate arrays, and they kind of
Well, you have an array for the nodes, and then you have.
Yeah, I mean that's how I would do it without the textbook. Just forget the textbook.
Well, yeah, I mean, you can make a data structure like for a specific node, and I don't know.
So you would use
You're not multiplying.
an incidence matrix or an adjacency matrix to create this with all the nodes by all the nodes to indicate where the weights go, and then you would take the weights and put it in like something like X, like another data structure. So like you can basically draw the whole graph from having two arrays.
Yep, I think.
And
yeah, I mean, I think
think
then
of
you would
X as
capture
like
all
the
data.
thickness of the.
Yep. I mean, yeah, I hear you. I'm definitely gonna need to. I know you're crunched for time. I'm definitely gonna need to go over this a little
Well,
bit
this makes
more
some sense, right? Because
on
like
myself.
the arrows point in whatever direction. So if they're one,
Why don't we meet again and then we can work on this? We can just do a coding session and then just go all the way through this chapter, like really well.
Yeah, I would like that too.
Yeah, I'd like.
And
to
we can like build some of these things that they don't have in the Julia Companion, because the Julia Companion is super light in this chapter.
Oh, is it really? Oh, that's
Yeah.
unfortunate. Okay.
Yeah. I mean, I
They
think.
they show you how to rotate, so they create a rotation. Then they do selectors,
Okay.
which is they do a reversal, which is the same as that mirror, or if you're trying to draw a shadow, that was one of the examples. They kind of skip over a lot of this. Then they do a permutation, but there's no
Yeah.
point in looking at the permutation example.
Yeah, I mean, this would be this. I think you were definitely right to point out, like like a water system or something.
Then they skip networks and they go straight to convolution.
I feel like that would be a lot easier to visualize this. I mean, I get the big picture of what's going on.
So let's like, why don't we meet and then we can write functions to do all of the stuff that's missing from the textbook.
Yeah, that X vector or that X thing, that makes sense why it goes around in a circle. I don't know if you guys kind of. I mean, like just X2 gets flipped around and the rest, and X4 goes away, and then you just have a clockwise rotation. X2 gets flipped around because of the -1.
X2 gets flipped around.
Yeah, because right.
Oh
so,
yeah, it does.
So that's what they're saying. Like, oh well, this corresponds to a clockwise flow on the outer edges. So you have, if you follow the arrows and you have a 1, it means you're going in the direction of the arrow. But if you have a -1, it's against it.
Yeah, exactly. So like you basically have the nodes, their connections, and the strength of those connections. And that's everything.
Okay.
If you're going to build it independent.
So X2 is the only. I mean, obviously it says it here, but but we can see it visually. Okay, that was good. So X2 is the only thing that's not going in a clockwise
right
rotation.
But if it's
Yeah.
-1, it is. So that and so the flow corresponds to uniclockwise flow. I don't know. It says the vector is a circulation. So I guess it just means it from any one of those nodes, if you were to start at that node, or any one of those edges, if you were to go along those edges according to those Boolean values, not Boolean values, those ones, -1s, or 0s, you would end up with a clockwise rotation, no matter where you started.
Yeah. And so for next time, install Jupyter Notebook, and we'll go through Network X too, and we'll do it. We'll try to do it the books way, but if we can't write it, we'll at least learn how to use a package.
Yeah, we could actually. Yeah, that's true. We could pretty much do anything that's graph related with Network X. Okay, that's a good idea. Yeah.
Yeah, I think that's.
Yeah, we could visualize it. We could do it. And I've been working with it, so
and then I can
help
send you guys a
visualize it.
video on what the eigenvectors stuff.
Sure.
Yeah, that'd be
So like one of the examples that's in the video. So this is a video from a class I took, but I still have it, and it talks about creating the most complicated versus the least complicated network, because you see how all those nodes could be connected in different ways, right?
Yeah.
So like sometimes you have starting data where like forget all the obvious examples like piping systems, GPS, stuff like that. Imagine you have a bunch of movie genres and movie topics or something like that. And those are your two edges. I mean, those are your two dimensions of a matrix, right? So there's a way to create a network from that, which is a different application of using network diagrams. There's a most complicated network, which would be like a star, and a least complicated network might be like something like a circle. They can form into different things. So there's other applications of this other than the obvious applications. What comes after this? So we
It's
can do a
I
convolution
think.
example too.
Yeah.
So we'll go through
Control.
Jupyter Notebook and like pull in packages, because I think the packages are going to work better.
Definitely. This flow conservation thing makes sense because if you kept x2 as a 1, you wouldn't have that flow conservation, and like you'd sort of be stuck, right? You'd be hitting 4 and stopping, hitting 4 and stopping, hitting 4 and stopping. So
Yeah.
4's inflow would not be the same as its outflow because it goes around in a circle. It has that conservation, and then they're saying basically that the product y equals ax y equals 0.
The question is, were they
so-
saying above that 1 flowing to 4 is actually 4 flowing to 1?
Yes, that's the way I'm interpreting it, because they're saying
Because there's
that,
like an arrow pointing to 4, but it still goes.
yes,
to
but that's the point, right? You have this edge that is pointing one way, so you have this incidence matrix, which tells you the directions of where these edges are pointing, and then you have this flow diagram, this flow vector that's telling you, oh, it's going in the opposite direction, right? It's saying no, the flow is actually going against what your incidence network was telling you. You know what I'm saying? So like, if you look at the incidence matrix as a not static thing, and you look at like this kind of thing as being able to manipulate that, then you can see like the flow can go against your incidence matrix or whatever.
I have really good videos on
Which
this
it
stuff.
makes total sense though. I mean, if you took your incidence matrix and you multiplied it by this x vector, the idea would be that it would equal 0. It makes sense, right? Like,
Yeah, it does. It does make sense.
Yeah, like, and that's what the conservation of the flow would. I'm starting to really understand this now. So Shane, that x vector you have there, multiplied it by the incidence matrix that makes up this diagram above you, and the idea, and this is what we should do. We should do it.
Yeah, for every single example too. It's all of these matrices stuff is phrased y equals a times x. It's always like that.
Okay, so I think that was a good explanation, and I'm starting to get it. So this x is what makes it a circulate. So this network diagram, the incidence matrix for this diagram exists independent of this x. Right. And this x is a circulation.
I don't want to call it independent exactly.
Okay, yeah, maybe not independent, but it
because the ones imply, like, if basically.
Let me tell them to wait. I'm gonna.
If they were all ones, though, Shane, it would be exactly what you see in the picture.
Yes, yeah. So then they kind of construct this X to create the circulation.
Correct.
That's a better way
Correct.
of thinking.
And if in the point,
so that's why when
the test was, I know Michael's got to go, but what we should do before we close out is just prove that AX equals 0 on this.
Do they give us the incidence matrix?
We can make it. We can make it though. We can make it, right?
Okay. I'm starting to.
So it's small enough that we can make it. So
This flow crystal. It's the unit.
So
Okay.
each eye is a node. So just make like you make four rows. Actually, they do give it. They do give it to us. It's that one up there, right? Like so.
Oh, it's this one.
I think so. So it's saying that I don't know why 1 1 is -1. That I don't really understand how an incident.
That's what I was. I mean, that's what I was. This -1 you see in 1 1. That's saying it's pointing to itself, but in like a negative way, right? So but if you're pointing to yourself, direction doesn't matter. So that's exactly equivalent to just putting a 1 there, I think, right?
Well, they say that's the incidence matrix. So let's not do anything.
That's an adjacency matrix.
They say the incidence matrix for graph.
Yeah, incidence.
Saying just take that matrix and multiply it by the x vector. That's all. That's all we're gonna do, and then we can
let's
finish.
do that. I got like 10 more minutes. So.
We'll just be 2 minutes because we'll just take this matrix, just build this matrix out. Just do A, and then just do spaces in between everything. So -1. Yeah, exactly.
1 0.
Right.
0. Oh. 0. And then you're saying we're going to end up getting 0 because of this?
Yes, because of the flow.
Okay.
The conservation of flow. It's actually kind of all right. Just make sure that that's what it says. Is that?
Yeah.
It looks right.
Yes,
to me.
it is. It is.
All
that
right,
is
cool.
it.
So make
an conservation.
Yep.
So is there always
no?
There's not always
if you got anything other than 0, it would not be a conservation. The conservation
so
means
this
that
is
everything
equals a times x.
Just make x. Don't make it a tuple. That they wrote it as a tuple, but don't do that.
Yeah. So no, what I was saying for any network graph is there always a circulation?
Oh,
Probably
I don't
not.
know. That sounds like a proof.
It
Right
might
there.
be though.
Yeah.
We have a 4x5 and then a 5x1. That should work, right? Boom. Yeah, and then you get straight zeros. Nice job. Okay, that makes me feel a lot better.
Wait, so what did we just prove?
That they're conservation of flow, because the every single node's inflow. Like if you look here, Shane, show your console again. Every single one of those was a 0. Which basically means so basically that means that node 1 has a conservation of flow.
The same amount went in that went out.
Exactly, of every single node. They all have a flow conservation of 0.
So now that only happens when there's a circulation then? Yes, right?
I don't know. I'm not gonna make any kind of big statements here. I'm just saying that every inflow has to equal every outflow, and that's a conservation of flow.
Okay, what I think we should do for next time is try to replicate all of these graphs.
I agree. Totally agree. And I'm down for that.
And we could do stuff with images, too, at the end of it.
If we're going to do it, I know you want to pull in Network X. Just give me a couple of days or give me a day, and I'll find the appropriate Julia packages, and I'll get enough toy with them so that we can always fall back on Python. It's no big deal.
Yeah, we'll do it in a notebook so we always have something to reference.
Right, exactly. So, what's today? Thursday? I'm down for doing something tomorrow. I mean, if you guys want, I don't know.
I can do that.
Yeah, I'm down.
After work tomorrow or 5:15 again? Is that all right? 5 o'clock maybe?
Yeah, we'll do like a power coding session.
Great, that sounds great. I will look into the Julia graph visualization stuff. I'm sure they have something very good. In fact, I'm almost willing to bet that there's they might even talk about it in the Julia. So I might take a quick peek in the supplement and see what's up. But I'll explore a little bit.
Yeah, there's a lot of stuff here. This is like when you start getting into this stuff, you can go pretty deep into this.
Yeah. I'm excited because you've been talking about.
If we can end just being able to make all of these graphs.
I already know I can make it. Yeah, I already know I can make this graph. I mean, I've been working in Network X for like the past 3 weeks now. It's just like all day long, every day. Unfortunately, actually, no, it's really good. I really like it. Honestly, I'm kind of blown away, but But I'm gonna try to find the Julia version of it. All right.
Okay, cool.
So
Or we can
tomorrow-
do it in Python. It doesn't matter. Jupyter Notebook works with that
I'll-
language.
Yeah. So tomorrow, are we good?
Yeah, that sounds good with
Yeah,
me.
I'm good for tomorrow.
All right, cool. Yeah,
wait,
there's
sorry,
a
what-
graph
can we-
plot for
can we-
Julia.
Can you guys explain like, so I'm looking at I believe that this is the incidence matrix for this this diagram here. But how exactly do you derive A here from this? Because so here you have -1 in at the first index and then the second one. Where is that on this?
Yeah, so what does the book say about each node? It says that so if it's a -1, edge J points from node I. So in the case of the top one, that's the only one that I really kind of like, what the heck are they talking about?
So so J2, so 2 is gonna point to 1.
Wait. J.
Or, no.
Sorry,
Yeah,
1,
yeah.
1, 2. So
Oh, look at it here. Yeah. That's
So-
better. So where is this? So you're saying 2 points to 1, or no? It's the backward.
Question is why?
yeah,
is it five
It's
columns
1
here?
points to 2, Shane, because
Yeah,
it,
1
it-
point
It
to
says
2.
that edge J points from node
Yeah,
I. So
one points
so
to 2.
J in
So
that
this
case-
isn't represented on the diagonal here. Isn't represented on this graph. We don't see an arrow that goes from 1 to 1.
yeah, it's a self-directed loop. I don't know about that one. That's the only one that I'm kind of like, what is going on there? I don't.
And then right here too, 3 and 3.
Yeah, I'm unsure of when the node is it's well, it's not only that, like I and J. Oh no. Okay, J is the edges. J's are edges, they're not nodes.
J's edges.
Yeah, there's 5 edges.
The nodes are the rows.
Because there's 2 different ways to think
Oh.
about these network graphs: is as a set of nodes or as a set of
Yeah.
edges.
Exactly. So
Yeah.
let's just look at node 1, for example. Node 1 has 3 edges. It has 1, 2, and 4.
Yes.
1 and 2 are leaving node 1. So it has a
Yes.
-1. Node 4 is coming to 1. So it has a 4. So let's look at 2.
Oh.
2 has 1 and 3, right? So
Yeah.
3 is leaving 2, so it has a -1.
Yeah.
It's coming to 2, so it has a
Yeah,
1.
yeah,
And if you think
yeah,
about it,
yeah,
it's like,
yeah.
if you think about it literally like in terms of
Yeah.
surplus or leaving,
Yeah.
right? Like if you
There's-
think of it in money, right? Money is leaving or coming to you. You have positive value
Yeah,
coming to you,
yeah.
negative value. So this makes total sense, actually.
So each column is always going to net out to 0 as well. Is that true?
So each column is an edge, right?
Yeah.
So what you're saying,
Wait, is that even no?
But how do we know what nodes
Shane,
it's
Shane, that's a
connected to?
But hold on. Shane, what you said is true, but it's true because it can't possibly ever be false.
Well, yes.
You know what I'm saying? Because you
The
literally are leaving,
rows are the.
you're leaving
I
one
think the
node and
rows
going
are the
to another
nodes.
node. So more importantly,
It's easier to look at it like you said.
well, it's not just easier to look at it. If
each
you look at the
row.
edges in a directed graph, it's leaving one node and going to one other
Yeah.
node. So every
Yeah.
single edge is going to have a 1 and a -1. It's not
But
just
how
that
do you
they
know
make-
what nodes that they're going to?
the
if
rows
it's
are
like edges?
nodes.
The rows are nodes,
yeah,
and the
yeah.
columns are edges.
Yes.
So every edge is gonna have a 1.
Let's
and
write that
-1.
down.
Yeah. That's
The
great.
nodes-
That's great.
The nodes are rows,
You
and
can't.
the columns are edges.
You can't have an edge unless you can't have an edge that doesn't leave, or
The only one that I can think of is the one
an edge that points to itself. Right.
Exactly. That,
So
but,
if you have
but,
an edge-
but I feel like that still maintains its own flow. Like you can almost like eliminate
It
that.
would almost have a 1 and a -1 at the same.
Yeah.
the same node
So
or
you would
something.
almost right. It's almost like a complex number. with
Yeah,
a zero.
yeah,
It's like a
yeah.
0 plus I.
Okay.
You
Yeah.
know,
this-
So the zero balance applies to the edges,
Okay.
and it doesn't apply to the nodes itself.
Correct.
Yep.
Okay.
Yep.
But
yep,
somehow,
exactly.
but you can take this system and multiply it by a flow, and that flow could still zero out the system. So in the case, I forget what x's we had. We had what was it, 1? So it was 1,
Negative
1,
right here.
1, 0. Yeah. Yeah, so like
Yeah.
somehow that flow, I mean, I don't have an intuition on looking at that matrix at what kinds of flows would zero it out. Um,
Well,
but
also,
I could guess, you know. I
so
could
another
guess.
one would be x1, x3, x4, right? So if you had 1, 0, 1, 1, 0, that would also be a circulation.
Say it
right?
again.
If you had 1, 0, 1, 1, 0, then that would be this circulation, which x1, x3, and x4. That would also be a circulation.
So one, wait. Where does it stop? So you're saying 1,
Yeah.
so 1, 0, so 2 doesn't
Yeah.
do anything. Oh.
1,
You're
1.
switching out the 4 for the, you're like, wait, hold on. So what did it say it again? 1?
I said 1, 0, 1, 1, 0. I think would also be
Yeah. So 1, 0, 1, 1. Yeah, exactly. Yeah.
Okay.
Yeah, if
I'm
you took
getting
the
it.
totals from the each row, though, you get the balance on the nodes, and then you know how much is.
Right. That's what I think too. Right. Like, can you just look at that for a second, Shane? So the console.
Sorry.
So what he's saying is add up, like, so in the case of the first one you'd have a -1. In the case of the second one you'd have a 0. In the case of the third one you'd have a -1. In the case of the last one you'd have a 2. So somehow,
And all of that should add to 0. Well, it doesn't have to. It could be.
Well, this
Yeah,
is for
I mean,
this is for the current graph right here. So this doesn't add to 0 because
no, but he's right
that's
though.
a
Like,
4.
if you can make that add to 0,
yeah, then you have a circulation.
then you've basically got it. So if
Yeah.
you
I
could
think-
take that vector of sums, I think I understand what he's saying. Like, if you take that vector of sums, and then you could sort of do a dot product with another vector. Yeah, I think that's right, because if you so what was it, -1, 0, -1, 2, right? So -1, 0. Oh yeah, that's weird because yeah.
It is sort of weird because.
So,
Yeah, you'd have to figure out. Yeah, it's still you have to figure out.
so I
like,
think, I mean, just visually, there's only 3 possible circulations here, right? For each loop. You
so
have,
you have 1, 3, and 4.
one-
You could do 1, 2, and
Yep.
3, and 1, 2, 3, 4.
yeah, so there's only 3 possible. And we just outlined 2 of them, and the other one would be
Yeah,
this
I
one.
agree. I don't see how.
Okay.
We'll play around with it. I think we're gonna end up writing our own.
There's 3 possible, Shane.
Like Network X probably doesn't require that much effort to just write it.
Shane, there's 3 possible, but there's actually more than 3 possible, right? Because you can do 1, 2, 3, 4 all in a clockwise. You can do them all. You can do each of them in two clockwise or counterclockwise.
Is it? But
So
for
there's 6. So
circulation?
there's 6 possibles.
Yeah.
Think about it.
Okay, so that's still a
Think about it.
circulation.
If yeah,
It's still a
so if I took
circulation.
X and I made everything in X negative.
Yeah, I hear you, and I yeah, it totally makes sense. You can take X and make everything negative, then you get a counterclockwise circulation.
Exactly.
Um,
And you could do the same thing with the other 2 circulations that you're talking about.
Yep.
Yeah, we're definitely gonna do this.
yeah, it's cool.
Yeah.
I
Yeah,
like
this
it.
is no. I feel I was so.
I'll try to find a cool. I'll try to find interesting data. If we could just find some data, this whole thing would be fun.
Oh, it could be
Even like a visualization for this, like a 3 blue 1 brown for like flow conservation would be.
He might
you know,
even have it, dude. So
you
all
would
right,
draw-
all right.
you would draw
We'll
out
break
water.
off into our corners. We'll try to find good visualizations, good data, like Michael said, good libraries. I'll do my searching for Julia, and we'll meet tomorrow at 5:00, and we'll try to do some really cool
Do
stuff.
something.
Because
Yeah,
I
I'll
think
write
we all
some
know
code
that there's
tomorrow.
really cool stuff in this chapter, We just and we don't want to screw it up. We just want to really, really understand it because it's really awesome stuff. I think
Yeah.
Yeah.
it's even got convolutions next, so it'd be really nice. So like, even prepare yourself for that, I guess.
I can show you how to do those convolutions
And 3 Blue, by the way, Shane, has some really good rotational stuff too. Like we have just if you can get a GIF or something like that, or something that just shows it nice.
Well,
let's
all of
compare
that's
ourselves.
easy. Everything in the that they cover in the textbook is like a joke. Like they did